All right, good afternoon. Welcome to the second lecture for week 7. All right, first some reminders. We have 2 weekly tests due 9 p.m. today. So with Flexibility Week, the week 5 weekly test was delayed. You've probably done it already. If you're sensible, you've done it already. But if you haven't, week 5 had a weekly test, do it. A weekly test also came out last week. Flexibility Week had a weekly test released, due today as well. Both of them you're meant to take an hour for, so that should be fine. And the assignment. The assignment is the big thing. Substantial amount of marks, due Monday 9 a.m. 9 o'clock in the morning Sydney time, Sydney Daylight Saving Time. Dylan tells me we've had a record number of questions in the forum and saying, can we put on more tutors? And I said, yes, we're going to try and find more tutors for help sessions. There is a problem that tutors are getting busy with their own courses, but we'll see if we can find a couple of tutors who can help out with help sessions. Just a reminder, Course Forum's great where you've got a problem that sort of, what does this error message mean? What's going wrong here? Something that can be answered in a few lines. Help sessions are great if it's general advice, interactive about your program. We won't complain if you ask something in the forum that's better answered in a help session, but don't be offended if we say, oh no, look, I think you better go to a help session for that. All right. And also it can be useful to scan the forum, see if someone's had a similar problem to yours. All right. And this, by the way, looking at the chat, this is not the boring part of COMP1521 coming up. This is some really interesting stuff we have to cover starting today. I love some of the stuff we've got to cover today. All right, so that's where this week's lab is our last lab on the MIPS, by the way. So you're writing some stuff in the MIPS. So now we're leaving assembler. Hopefully, you've got this lovely understanding of what the silicon of a computer actually does, what that little complicated world living in a few millimeters square of silicon, how it works, what it does. And this informs your understanding now of things like debugging a C program or what makes programs run faster or slower. But now we have to move higher up past the hardware software interface into the lowest levels of software that talk to hardware. So we're going to talk about files, but we've got to lead into it with a few things before we get to talking about files. First, I guess, what's an operating system? It's software. Examples of software, famous ones are, for example, Linux and Windows. OXX is another piece of software that you might be using. Android, if you might have the operating system for your phone. Well, it's a bit more than an operating system. It's plus operating system plus sort of surrounding applications. So it sits between the operating system sits between the user and the hardware. What does it do? One way operating systems people like to think of it is that an operating system presents a virtual machine to each user. So rather than all users fighting over one real machine, interacting with each other, causing problems for each other, they see a virtual machine which isolates them from each other. We'll talk more about that as we go on, but that's how the operating system is how we can have on a CSC login servers 100 students, each who seem to have their own machine. This virtual machine can be much simpler and more convenient than a real machine. If you actually want to send bytes to a disk, it's a very complicated operation, and it involves unpleasant low-level timings, changing bits, knowing about disk formats, all sorts of things you don't really want to know about. Whereas the operating system can sit there, do that for you, and all you can have to say is send here's 512 bytes. Send these to the disk. So convenience, simpler. There's one huge other thing that we get with Linux in particular. It can give us portability. So some operating systems run just on one or perhaps just a couple of pieces of hardware. Windows is a classic example. It used to run only on certain Intel chips. They've ported Windows to a few more architectures, but it's limited in the architectures it can run on. But Linux runs on almost anything.
And then Windows 11 was released, and they squashed that right back down again with some of their hardware requirements.
Oh, really? I didn't know that. Thank you. By the way, in the chat we have Dylan, Jashank, and Zach.
And also, interestingly, Windows NT was actually designed to be very portable. A lot of the lessons learned in Windows NT's design were learned from, in fact, I think building on a MIPS or on MIPS processors.
If you talk to operating systems people, they have a fondness for Windows NT and its underlying design. Yeah. All right. So Linux runs on almost all suitable hardware. We'll talk more about in later lectures about what makes hardware suitable, but basically it needs extra features beyond what we've seen in writing our MIPS programs, particularly in dealing with memory. In the MIPS programs you've written, it's as though you can write to all memory, and that would be disastrous if we had 100 students on the one machine who could write to any piece of memory, even if they were trying to be nice to each other, which I wouldn't depend on. They would accidentally write to memory belonging to other students when their programs went wrong. And you've seen that. You've written MIPS programs that have actually tried to write to the wrong piece of memory and failed as a consequence. So any general purpose computer, anything that's sufficiently powerful, Linux is basically available for it. Linux is free. You need an operating system, you port Linux. If your computer is small, tiny, the sort of thing you put inside a toaster, it probably doesn't have the features to run Linux. There are limited sort of operating systems barely worth talking about as operating systems you'd use in that circumstance. But it's pretty amazing. I can write a Linux program for assuming Linux and run it on so many different platforms. We'll talk a bit more about portability with file operations later in the lecture. So yeah, this ability to have multiple users is an amazing consequence of an operating system, and it's enormously useful even if there's really only one user, one sort of person associated with a device. So many people have laptops, and there's only really one person ever uses the laptop, but having multiple users in the software is an enormously useful way to organize things. Same applies to your phone. You may be only the person that uses your phone, but we can still share your resources between different sorts of processors. Why do you want to do that? Well, one reason is you install apps on your phone and you want to limit what those apps can do. Yeah, privileges and security. Yes. Yeah. So that's the sort of job of an operating system. All right. Yeah, let's. You can delve into this. If this stuff is sort of whetting your appetite, you're thinking, this all stuff sounds cool. Set a course to take our operating systems course, which is COMP1521, and even then perhaps our advanced operating systems course. Arguably both the pair form good at operating system courses you can take anywhere in the world. So even if you're somewhere like Carnegie Mellon or Berkeley, I'd say the operating system courses aren't going to be any better than those two. But then it's for someone who wants to explore those sort of things. All right, so they'll tell you that this is a gross simplification, what I'm talking about to show you in this slide, what I'm showing you in this slide. But it's a useful one. So for an operating system, we need to have some way of there being two modes of operation. The operating system we want to run in a privilege mode where it can do anything. It can access any bit of hardware, it can access all memory, it can do any operation we want. We also need a non-privilege mode where we can run ordinary user programs and they can't do these things. They can't access hardware at all. If they want to send bytes to a disk drive, they've got to go via the operating system. If they want to access any device, they can't do it they have to make a request to the operating system, so the operating system can verify that this request is something that they're permitted to do. The other thing we've got to do is we've got to give them limited access to memory. So if they're in, if the code running in the non-privileged mode tries to access memory that's not associated with it, doesn't belong to it, you might say, it doesn't happen. The other thing we need is the ability to switch between the modes. So the operating system has to be able to launch a program, a process in non-privileged mode when it wants to run a user program, and a user program has to get some way of getting back to the operating system. It has to have some way of getting back to running code in privileged mode, but the operating system code, not the user's code. That way of getting back to the operating system is called a system call. It transfers execution to operating system code. So you make a system call, you get privilege mode. That's the good news. But it comes with, it's not your code that runs in privilege mode, it's the operating system code. When the system call completes, the operating system, when it's done whatever you asked, will usually send execution back to your code as a user, but back in non-privileged mode. So a program could be sort of flipping between privileged and non-privileged mode. Again, this is a huge simplification of the world of operating systems, and there are endless possibilities here and all sorts of clever things, which you can explore in further courses if you'd like. All right, so system calls. That's going to be we're going to look at system calls in great detail over the next half an hour or so. System calls. It's a request. So what happens with a system call? I've said it goes to operating system code. I said it goes into privilege mode. It'll include arguments saying, I want to do this. I want to write these bytes to this file. So a key thing the operating system's got to do is check, well, is this valid? Does this make sense? If they're writing bytes to a file, does the file exist? Is the address of the bytes you've given it really an address in memory you own? That sort of thing. Is it permitted? Maybe the file exists, but it's not my file, it's Dylan's file, and I don't have permission to write on it. So it's the key thing it's got to do is check this is valid and permitted. This is a gigantic thing if you're writing operating system code. You've got to be completely paranoid. You've got to do these endlessly careful checks on the parameters you're given for a system call. The user's request to do X, you've got to check so carefully that everything is something that user is allowed to do. Assuming that's true, the operating system will then somehow carry out what's requested. Add those bytes to the file, send those bytes out on the network, create that program and so on, and then return execution. Now, we've mentioned different operating systems. The system calls are completely different between operating systems. So if you learn the Linux system calls, some of them might have somewhat similar Windows system calls, but in general there's just no commonality between operating systems. It's a very specific thing to the operating system.
It might be worth adding here, if anyone's used an interesting program like Wine, there are projects that sort of try and add these compatibility layers between different platform system calls. So a really popular one being Wine is a compatibility layer to try and translate Windows system calls into Linux system calls, so you can run Windows, more or less run Windows programs on a Linux machine. And if you've used like Steam's Proton, I believe they call it, that's their sort of fork, or they built on top of Wine or something like that. So there are efforts to try and make these sort of layers between these different operating systems and their system calls in a very simplified
and vice versa.
Yeah.
And vice versa as well. Windows system for Linux, Windows subsystem for Linux, or Windows subsystem for Android. Chrome OS has a bunch of stuff like this, etc., etc. This interoperability is extremely powerful and very interesting to develop as well.
It's an interesting question how well it works, though. I don't know how good Wine is these days, but in the past it was never quite there for a lot of. There were little programs you could run, but it seems like people are doing more these days. Fortunately,
Yeah,
I
Yeah.
haven't had the.
and Steam's
Mine's-
efforts on Proton have been quite incredible in getting
Yes.
many of these AAA
Yeah.
big video
Yeah.
games to run
Well,
perfectly on
actually,
Linux.
Steam is fairly confident that in the next couple of months they'll be able to get Proton to run every game in the Steam catalog. So they have some pretty high hopes for what is effectively just a little wrapper around Wine.
So I'm pretty amazed by this. So what we're talking about is that you've got a computer games which make heavy use of interesting system calls, and Wine, or this version of it, will get the Windows system call and translate it somehow into equivalent Linux system calls, and there's a big gap between them. So it's a very clever thing to do. All right. And Jashek, Windows subsystems for Linux, I have used a little. It seems to work quite well, but I've only tried to do quite simple things where I get a program from Linux that makes Linux system calls, and they get translated into Windows system calls, and it creates files and things like that, and that seems to work quite well. All right, so yeah, there's some classic examples for you of the sort of things you might request in a system call. You might say, send this information on the network, create a new program and run it, give me some more memory, read or write some bytes. So classic sort of system calls. All right, now you've actually seen system calls already, of course, in SPIM. So SPIM and MIPSI matches SPIM. SPIM provides a tiny little operating system as well. So SPIM does two things. It emulates MIPS instructions. We want to run MIPS programs, but we don't actually have MIPS silicon, so it'll emulate it. That's great. But it also provides a tiny operating system. So this is both good and confusing. The good thing is you access the tiny operating system on SPIM just the same way you would if you had a MIPS CPU in Linux. So the syscall instruction, that's not some pretend thing in SPIM. That's a real MIPS instruction, and if you have a real MIPS CPU like Jashank, and when a system call needs to be done, it will execute a syscall instruction. It will pass execution to a certain address where there's operating system code, and the Linux operating system code on the MIPS will look at $V0 to see what request you're making, and $A0 to see what argument you might be displaying as the first argument, perhaps like $A1 or A2 if there are more arguments. So that's all very real. Okay, what's fake? Well, what's fake? What's toy? That's a better word. Pretend, toy almost. Is SPIM system calls are designed for students writing tiny MIPS programs, and you don't without any helper code, without any library functions. So they give you things that are really useful when you're writing that 20-line MIPS lab exercise. One is, system call 1, print an integer. System call 5, read an integer. They're sort of specific things, and a real operating system wouldn't have such a specific system call. Well, not in the last 50 more years at least. Yeah, so a real operating system might say, read n bytes from this file, write n bytes to this file. Normal people coding, normal programmers, don't access system calls directly at all. They never see the system calls. Almost all coding, you're actually using functions. When it's time to say print an integer, you call printf. And printf actually won't make the system call. Printf will probably call another function, which will call another function, which will call another function, which then might call assembler that does the write system call to write out the bytes of the integer.
_printf internal _int is the internal function that will be called.
So
this is implementation dependent, of course. There are many implementations of the C library that take advantage of different system calls.
All right. So, but we're going to poke down, and do things that the normal programmers don't. So we have this understanding of what's happening in the lower levels of the code. All right. So let's go a bit deeper in this. Oh, so Linux. I've said Linux provides 400 system calls. Can I copy this? Oh wait, no. Apparently I can't. Thank you, Ocular. But I can. That was user include. Was it Unistud? What was my... Oh, ASM Unistandard. We can find out all our system calls. There they go. Alright, this isn't the file that you'll normally use, but this is all the Linux system calls apparently on this platform. There's some system calls that occur on particular platforms only. I don't think we need to get into that. Each system call has a number. So right at the first, system call number 0 is read, and it's read a certain number of bytes, and write is write a certain number of bytes. So system call 0 and 1. Let's go to the bottom of the file and see what's down at the bottom. System call. Oh, these are some new system calls I think that have been added into Linux relatively recently to do interesting things. And these are oh, I'm looking at these system calls, and most of them I can't even guess what they do. So they're really specialized system calls mostly.
I'll hold up my handy dandy "is that too many system calls" card, because I think that's too many system calls.
So go along to COMP1521, and I'm sure Kevin will tell you why that's too many system calls. So we're not saying, yeah, I wouldn't, and I think I'm in Kevin's camp here, but don't worry too much about what these are and what the number are. We're just going to poke it around at just a few of these ones, these early ones, and play with them. So there's a whole world there that doesn't really worry us. Oh, well, look down here though. That one's nice. You want a pipe? There's a system called create a pipe. Yeah. Come along to COMP2041 and we'll use that system call to great effect. Alright, that was fun. A little scary. Let's go back a bit. Yeah, we've seen every... So for our enjoyment, again, this is not something people do normally. There is a C function syscall, which allows us to make a Linux system call without writing any assembler. It's quite nice because then you don't need to know exactly what platform you're on, and it'll work more or less if you run on different platforms. That function itself will need to be written partly or entirely in assembler. If you go to that URL, which I've tried to link up and got the markup wrong for, if you go to that URL, you can actually see the source for the system call function on this platform. It's assembler. It's Intel assembler, so I won't show it to you. But that means we can call this function and we don't have to write our own assembler. You can, by the way, embed assembler in your C program if you're feeling brave. If that sounds interesting, after the exams, Google and you can try playing with that. It's sort of interesting and sort of not.
There's also the far more interesting underscore syscall, which is basically, I don't want all these niceties that make this system call function work on multiple operating systems. I just want to directly do a single system call because I know it exists, hopefully.
Hopefully. All right, let's show you using syscall. I think I've got some. Yeah. All right. So here's a little program. What does it do? It creates an array of bytes. Now, what does double quotes mean in C? Let me remind you. Double quotes in C means char array with ASCII values. So I've put in there's 15 characters in that string. You count them up properly. So I get a char array with 15 ASCII values. The second last one will be a 10 for the new line. The last one is there's a terminating 0 byte added. So I'll get 16 bytes which happen to contain ASCII values. That's one thing I've got. Here I've said do a system call. I've nominated the number of the system call. So that could be any number from 0 to 448, depending on which system call I wanted to play with. And I've given the system call some parameters. Now each system call will have a different number of parameters. Some system calls might take no parameters. trying to think of a system call with no parameters, but certainly they take a variable number of parameters. For a write system call, I have to specify where the bytes I'm writing going. One is sort of a special value. It's a standard output stream which I expect to be set up going to the output of the process. The second argument is an address in memory of where the bytes are I want to write, and the last is how many bytes I want to write. Notice there, by the way, write doesn't do anything with ASCII or zero termination. I have to say how many bytes. And this is important because I may want to write binary data. I may want to send binary data to a file which might have zeros in it, might have non-ASCII values. I can send any bytes with write. Alright, fingers crossed.
The first one I can find is the getID system call. GetTID does not take any parameters.
Okay. What is a TID? One has to ask.
Thread identification.
It's a PID, but spelled differently.
It is.
Ah, okay.
This is Linux, of course, so yes.
And there we are. So by doing this, I've said to the operating system, write these bytes, and there they are. I've got the ASCII for hello Andrew, and my terminal has rendered it as the appropriate characters. That's beautiful. So that's making a raw operating system request. If you follow that link, you can see sitting behind this there's actually about 10 lines. Maybe a few assembler instructions. Yeah. All right. So that's making an operating system request. All right. Oh, here's using. All right, we'll go to my next example then. Let's try doing a couple of operating system requests in a loop. So I'm doing operating systems requests 0 here, which is read bytes, and 1, which is write bytes. Now some of you are saying, Andrew, that's poor style. You should be using hash defines. Yeah, I really should be hash including that file I showed you earlier with names for the Linux system calls. But I thought it's actually clearer to see that really I like showing it just as raw numbers here, because it's clearer that the thing is a number. But if they ever decide to change the number of these system calls, there will be a problem for my code here. Alright, what does the read system call do? Its first argument is where to read from. This is a file descriptor. File descriptors we'll talk about quite a bit more. They're small integers which we get from the operating system and we give to the operating system. So they're a way of they're like a label for us, or something we can say to the operating system what file we're talking about. We'll see more about that. 0 is a special file descriptor which is standard input. So a read system call, I have to tell the operating system where I want any bytes read put. So I give it a memory address and say I want to read some bytes, put the bytes at this memory address. And here's my memory address up here. I have to say how many bytes I'm willing to accept. I've said, look, give me 4096 bytes. Now, it doesn't mean I'll get 4096 bytes, but the operating system won't give me more than that. Now, the operating system can't check that, like DCC, that this will be within the array. It will check the memory belongs to me. That's all it'll check. So the operating system will say, all right, I have to give Andrew these bytes. He said put them here. Does that memory belonging to Andrew? Yes it is, and it'll put the bytes there. It gives me back a value which is how many bytes it managed to read. Yes, I'm not sure why that type is long. interesting point. Well, that probably is correct. What is the correct value for syscall there? Ah, it is too. All right. Interesting.
I think in this instance that should be an S size T, but that's neither here nor there.
Well, I don't know. I'm matching what syscall says.
Yeah, this is where the syscall interface providing you just a bunch of longs moving around versus the interface, the system call itself.
Yes, right. That's a fair point.
Different
This
parameters.
this is ugly. This doesn't work well. This just gives us a chance to see raw system calls to show us what's really happening underneath. So if I manage to read 57 bytes and then I write 57 bytes, then I sit in a loop until I keep looping until I can't read any more bytes. So let me compile that program. Get it to make system calls. So I'll run it. And it's now trying to read bytes. Oh. All right, and I can signal with Control D, end of input. So I just type Control D, which is it's an operating system way of saying I don't want to give you any more input. Bytes read would have been 0, and that loop exited. That was nice. Got one more. Oh no! All right, we do have one more, but we're going to get to it for a little way. Now we have to talk files and file systems. File is a word you've heard probably for many years, computer files and things like that. What is a file? The concept is a little operating system dependent. The most modern operating systems, I think what's here will apply, sort of. But Linux is pretty clear. A file is a sequence of 0 or more bytes. You can substitute array for sequence, and it would mean that you'd get a pretty good understanding what a file is. So it's just 0 or more bytes, one after the other. On Linux, there is no meaning for bytes within a file. So there's no way to say to Linux operating system, oh look, that's a video, an MP4, or that's ASCII, or that's a JPEG. The file metadata doesn't say that. Linux files, Unix-like files. So this is one of the great steps forward with Unix, was just to forget about having any notion of what's in a file. Just say files are bytes. It's up to user code to interpret those bytes. Simplifies the operating system. It was a great step forward for operating systems.
Yeah, you can do some very fun things with this concept in Linux. Essentially, how a file is read depends on the program reading it, which means you can craft files that can be read by different programs. I can have a file that is both an image and a PDF, or an image and an executable, or an executable and an archive. You can do a lot of very, very interesting things by squishing files together and merging different parts of them, and having one program read it one way and another program read it a different way.
So this sounds weird and strange, and it's true that people often playing with that just to do weird and strange things. But this actually also arises in questions with security and things like this. If people can sneak an executable past a firewall or whatever disguised as a PDF, that's not good. All right, but back to this. So yeah, there's nothing in the operating system doesn't know what's in a file. It just knows that it's bytes. Operating system does maintain metadata about files, information about files. Permissions would be a classic thing. Who can access a file? So there is metadata. It's just not semantic, is what I would say. It doesn't talk about the meaning of the file. System calls give you the operations to manipulate files. We're going to see low-level system calls, and then later on we'll look at a much better way in general. If you've got a C program and you want to work with files, you probably should be using the operations from stdio.h. And you've already been using some of them. You've used scanf, printf, fgets. They're all from stdio.h. In general, if you want to access files, they're your friend. They're efficient, they're portable. It's rare not to need to use lower level ones. I'm going to show you the lower level functions so you know that you're there. And if you're doing something like building your own database system, yes, you'd switch to using lower level APIs. You might switch, yeah, you'd actually switch to doing some, if you're doing something like a database system, you might switch to doing clever system calls as well. All right, names. One thing I try to get across students is whenever you're told, this thing can have a name, you got to ask yourself, well, what are the rules for that? What can I use in that name? What can't I use in that name? It's often an important consideration. So what are the rules for Unix-like file names? They're pretty general. So Unix-like file names, 1 or more bytes. And you can have any byte you like. All 256 bytes are available for you, except you can't have 0 and you can't have 0x2f. So they're both, you can't use either of them in your file names, sorry. This is a Unix-like thing. If you go to another operating system, it may let you have 0x2f or 0x00 in your file names. And this means file names are not necessarily portable between operating systems. In fact, there are classic issues and classic problems with transferring files between operating systems. So, why 0x2f? That's the ASCII slash, and it gets used in Linux path names as a separator. So it can't appear in the components of path names, which are file names. So you can't have slash, and lots of the interface code for the operating system uses 0 bytes to terminate path names, so you can't use those either. You're saying, well, can I use Unicode? Yes, what the bytes, and it's up to you really to interpret the bytes in a file name. So you could use Unicode. You can have Chinese characters you want in your file name. Sure, it's up to you to interpret those bytes. The operating system just knows that they're bytes.
The most fun thing that's missing from this list of things that you can't have is new line. You can have a new line in a file name. You may break some programs because it's not very nice to have a new line in a file name, but you can.
Yes, can and should, different words. So yes, you can have a new line in a file name. No, you shouldn't have a new line in a file name, but...
Come and take 2041, because then you'll hate the fact that you can have new lines in a file name.
But if you want to be aware of security issues, yes, you have to be aware that a file name could contain a new line. All right, there are 2 file names that are special and you're not allowed to use for your own files on Unix-like systems. You can't have a file called just dot. Dot has a special meaning. It's a reference to the current directory, and double dot is also special on Unix-like systems. It's a reference to the parent directory. So you can't create a file or a directory with those names yourself. Now, you might be aware that if a file name has its first characters dot, like dot profile, dot bash login, dot config, a few programs treat that specially. That's just a convention. That's not Unix. The operating system doesn't do anything special with file names starting with dot. Let me show you what I'm talking about here, rather than just waffle about it. So I've got these files. If I can create a file called .andrew. If I do an ls won't show .andrew by default. There is an option to ls, which I think is the -a option, to show this.
Dash capital A shows hidden files. Dash lowercase a shows everything, including dot and dot dot.
Well, there we go. Dash capital A. You can see it tells me now that .andrew exists, and I can also see cat underscore syscalls.c.swoop, which my editor creates. Why do these programs do that? It's not to scare. Well, it's mostly convenient. Hiding these is sort of nice. It just means that you can have files that aren't cluttering up what you see by default, but it's not part of the operating system. Right. Actually, let me check this out. Can I say to VI write the file ... No, it won't. But I can say I can create a file with 5 dots as a name. I shouldn't, but I have. All right. What's a directory? I've told you what a file is. It's one or more bytes. A directory is a set of files or directories. It is there. It's a recursive definition. So a directory is a set of files or directories. We access files and directories with path names. Absolute path names start off with a / and give us the full instructions for finding the file. So actually that really should have a hash. So if we want to access stdio.h, the source of stdio.h lives in /user /include /stdio.h. The crucial thing is there is /. That means start at the root of the file system. Now, we could do everything with absolute file names, always specifying everything to get to a file. So when we needed to compile a file, let me show you. What was the last file I compiled? It was this one. So this, I could compile that file every time by giving the full path name, which is here. Gets a bit tedious, doesn't it, if I have to do that? So it's inconvenient having to type full path names. It also is clumsy. It then embeds the whole path in if we use it inside scripts and things like this. So it creates a problem when we want to run this in various versions of a thing, if we're hard coding the whole path and everything. How is it then that I can compile a file just by specifying this? The reason is this: every running program on a Unix-like system has a current working directory. It is the absolute, starts with a / path name of a directory. If I don't specify a directory, that absolute path name is inserted before whatever path I give. So if I say cat syscalls.c, there's no / there, then all of this gets inserted there. Yeah, so here's what I'm talking about. If my current working directory is this, and I say main.c, it gets translated to this. If I can also use double dot in weird ways. So if I say double dot /a.out, it'll get translated to that, which is the same as one level up. So I can use double dot to maneuver around the lecture hierarchy. Let me show you that. So I can say ls double dot will tell me what's in my parent directory, which is all the directories where I've been putting lecture files. What I can do is could say compile double dot slash, suppose I wanted to compile something from yesterday. What was it, i0.c? Do it like that. So I can say, and that's the same as saying this. Just squeeze you across some room. Oh, come on. Oh, I put a space in there accidentally. There we go. And if you look at this, double dot sort of reverses the previous level, so I get it's the same as saying this. Go to the Tuesday. So that's double dot. It's an important thing to be aware of because you might make assumptions about path names, and double dot might break those assumptions. That's quite nice. All right. Right. So far, I've been talking about files as just arrays of data. And when Linux was done, when Linux was done and when Unix was done, it would be arrays of data stored on magnetic disks. These days, SSDs are being used much more. The files I just showed you are still being stored on a magnetic disk. Permanent storage. And the interesting step, a really interesting step that Unix took was to provide access to things other than data on disks via the file system. To use the file system interface as to ways to access things that are definitely not data on disk. So maybe you can access, you could access your mouse via a path in the file system, or your keyboard. You want to get data from your keyboard, you can get it by reading from a path in the file system. You want to get system information, you might be able to do that. You might be able to communicate to other processes via using paths in the file system. So everything is a file philosophy, really shaped Linux. It simplifies the system. Well, you'd say it simplified the original view was, it made system calls so much simpler, because a lot of the things you do when system calls in other operating systems were done instead through file system access. But we can see with Linux and its 440 system calls that perhaps it hasn't entirely been a win. Maybe I should show you some examples of this. What can we access via the file system that's not data on a disk? So there's a special directory on Unix-like systems /dev, which gives you names, typically things are put there which you can access, which are not files. Oh, what about dev random? I like dev random. Dev random gives me random bytes, not fake random bytes, real random bytes. So Linux gets sources of real randomness, which timing of things like this, and produces perhaps if you want cryptographic security, maybe you want to investigate further, but it gives you pretty solid randomness. And I can say read from dev random, and I'm not getting a file from a disk, I'm getting random bytes. XXD is a program we'll see in a few places. It's a very helpful program for printing binary data in a form we can see. So it just gives me random bytes, which won't necessarily be ASCII, and there we go.
if I was going to say, if you're just going to use XXD with no size, I would use urandom so that you don't exhaust your random pool.
I'm not scared of exhausting my random pool.
It used to be on much slower and older computers that was actually a distinct possibility. On modern systems, there's enough random folding and entropy coming in that it's not quite so hard, or it's not quite so easy to do.
So anyway, that's sort of that's a fun one. Just give me random bytes by talking to the file system. What else can I do? There's another place where fake file. Oh, I'll just show you.
Dev, by the way, stands for devices, and pretty much everything inside devices is not a file on disk. It's a device, which is something that pretends to be a file.
So these devices here are devices that would give me raw access to the disks on my system. So I could send bytes directly to the disks on my system rather than sending them to the files in the file system, which would be catastrophically bad probably. So I won't write any bytes to those. Let me show you a different files. Place for files.
My favorite device is dev/CPU, which, if you know what you're doing, you can theoretically send instructions directly to your CPU by writing a file.
Okay, I'm not going to do that either. Let me be clear about that. All right, here's another weird one. This one, if I read from this, I'll get a description of my processor. So there's no real file there. When I access this file, the operating system synthetically creates the bytes describing my processor, and it will tell me that's the processor I'm running, and it'll give me information about it and things like this. So if you can look at this to find out information about your processor. Can students run that on CSC systems? And then is that a non? Yeah, it must be a non-privileged thing. I haven't run it. So you can on a CSC system run proc CPU info and find out what the underlying processor is on the login server or VLAB or things like this.
There's also LS CPU. If that one doesn't work, LS CPU definitely does.
Well, there's one more I wanted to show you. I think I've got it here as an echo. No, I did that. All right, let's not do that then. I can't remember the command. Let me get it. I was going to change the IP forwarding on my processor, on my computer. Let's see if I can find it. There we go. Sorry, apologies for this. This file tells me whether, if my computer has sent a networking packet that's not for it, whether it'll transfer to the computer it really is for, whether it'll forward networking packets. So, not a topic we're going to cover, but I can actually change that by writing to the file. So I can change the operating system behavior. If I've decided I don't want to keep forwarding networking packets, I can change this file, and I'll try and do it, and it won't let me do it because I'm not root, and then I can come root and change it, and my computer will then stop forwarding networking packets. Actually I won't do that. I'm not 100% sure.
You're very brave for doing that during a lecture while you're streaming out.
Yeah, maybe I won't do that. I was just thinking maybe that's not wise. But if with root user ID, if I did that, I would change the forwarding of packets.
But the other question I'd ask is, then where is that stored? Surely that's not a thing that's stored on disk. Surely that's not something that's stored. So what's happening there?
So when you try and read bytes from this file, a a configuration variable in the operating system is accessed, and the appropriate bytes to represent it are returned. When I try and write bytes to it, that configuration variable is changed. So there's no real file. This is a way of changing the operating system. It's toggling the operating system. It's like a switch for the operating system. It just looks like a file, and you can access it like a file, more or less. It's the rather than have a special way of changing this to change, packet forwarding, we'll just put this fake file name there, and if you read it, you'll see what the current state is, and if you write to it, you'll change what happens. Can you do it with a text editor? I'm not sure. I think you might be able. Alright, that's the everything as a file. Don't freak out too much about that. Yeah, more for your information. We won't be going into that, sadly. We won't have time to really get into that. We will have time to explore a bit more about. Oh, actually, well, this is a good time to take a break. I think we're at 1 past the hour. Let's have a 5-minute break so everyone can get up. I can stretch. You can go to the bathroom or whatever. So we'll take a 5-minute break and come back in 5 minutes. All right, everyone, we're back. There's a great question in the chat from Niroda. I hope I'm saying your name right. Is it possible for file names to include a slash if you have a backslash before it? I can't say I'd actually ever really thought of doing that. And the operating system actually could do that. That would be possible. But it doesn't. Sorry. Linux just says you can't have a slash. There's no way of escaping a slash like there is in the text of a C program. So good question, good thought, but no. And it's just a design choice. They want to keep the operating system code simple, I guess. That's probably sensible. All right. So I said a directory is a set of files and directories. Does mean you need sort of a special directory to get started. The special directory has a weird name. It's slash. So slash is it's the name of a directory. Yeah. So it's the root of the file system. It often gets called. People often think of file systems as trees, so upside down trees, I guess. So that's the root of the file system. Now, if you've done, some of you, most of you probably haven't done a data structures course, but there's a concept of a tree versus a graph. A tree, in data structures terms, there are no loops in. You just head outwards, and you never go around in circles. Whereas a graph is a more arbitrary structure where there can be connections back. So, in a graph, there can be a connection that takes you, sorry, that's not right. If there was a connection that could potentially take you from here back up to here, so if you're trying to explore the file system, you'd go around in loops. That would be a graph. So Linux file system is a tree, doesn't have loops, except if you think about if you follow symbolic links. Symbolic links make it a graph. So you can have a symbolic link that takes you back up here. Don't worry too much about that. We'll show you I'm not sure we'll get the symbolic links today, but we'll show you symbolic links. Alright. Oh, another word for you. Oh, that's a word I like. Inodes. Every file has its metadata stored in an inode. I think the I stands for index. I've actually forgotten. But every file has an associated information in the operating system which stores information about the file. For the operating system, it'll tell it where to find the file contents. It'll tell it what sort of file it is. Is it a regular file? Is it a directory? Is it something else? And we've seen these weird files that are not files that in the file system, so it could say it's that. It will say the file size in bytes if it's a regular file. We've said regular files are essentially arrays of bytes, so the inode has metadata saying this file is 1015 bytes. It might say this file is Dylan's. It might say who can access the file. And a typical sort of thing might be the owner of the file, if it was Dylan, can do read the file, write the file, execute it, and Dylan might have set up the file so other people can access the file contents, read the file contents, but not change them. There might be timestamps installed in the inode, which are when the file was created, perhaps when it was last accessed, when it was last changed. So there might be timestamps in the inode. Now, file systems are incredibly, they do all sorts of things to improve performance. They add endless complexity to add performance, which we don't need to worry about. So yeah, a good example of the sort of weird thing file systems do is if you've got a file that's just 5 bytes, rather than storing its contents in a regular place, they'll say, oh, we'll just store that in the inode itself, because 5 bytes is much smaller than the information we'd have to store to put it somewhere on disk. Yeah, weird irregular things. So a Unix-like file system essentially has an array of inodes, and this array has the information about the files. Let me try it out. Let me try this out. So I've got my current directory. Let's ask it what the inode, ls has a -i option. You don't need it a lot, but it'll give you the I number. What does that mean? What is that? That's an index into an array, surprisingly. This file system apparently has a lot of, because that's 45 million, apparently this file system has a lot of files on it. If I go to index 45,640,594, I'll get the metadata for a.out. So every file has a unique number. Just like every UNSW student has a unique ZID, every file has a unique number. It's unique to the file system. Just like ZID is unique to UNSW, you go to Sydney University and there could be someone with the same number. If you go between file systems, and we haven't talked really about what a file system is, but if you go between file systems, I numbers could be the same. But otherwise, if I do ls-i, all these files are in the same file system, so they'll each have a unique number. There you go. They were created about the same time, hence the similarity in numbers. So that's I numbers. Yeah, weird things. It's how then it makes directories pretty simple. A directory just has to have in it effectively the name, a name, and an inode number. So it's a list of those pairs. If we ask the operating system, oh, I want to access this file, so I want to say I want to access a.out, it'll open the directory and scan for a.out. If it can't find a.out in the directory, it'll say not found. Otherwise, it'll find a.out and an I number, and then it'll go to the inode table for that and check, can I access the file? It might update the timestamps if I ask for the contents of the file, it'll use the data in the inode to access the file contents. That's all happening underneath, deep underneath. Oh. Two more sorts of file system objects. Links, hard links and symbolic links. Well, hard links aren't really an object. They're just a way of giving a file multiple names. Let me show you here. Which file? If I say, I don't know why you do this. If I say that, I've just given a.out another name. There are now two names for the one file. Not a copy. They're identical files. Any changes to one will change the other. So I've created a.out and out.a. Both will have the same I number. Yeah, we can see that, can't we? So I can say, oh, this is a name for this file and this is a name for this file. Is there a good reason to do this? Actually, not a lot. Yeah, it's not something you do very much at all. Maybe some manipulating temporary files or perhaps like that. It's hard to think of why you use hard links these days.
The one benefit that hard links have over symbolic links is they can have different permissions. So putting the same file into, I believe, can they?
I don't think so, because the inodes, they've got the permission.
No, that's true.
The one place I have seen hard links used very successfully, for those of you who have Mac laptops or similar devices, and you take backups like you should, Time Machine uses hard links to deduplicate content. So if a file hasn't changed between one backup and the next, you just make a hard link instead of actually going to the effort of copying the file again, and that saves quite a substantial amount of space.
Deduplication. Thank you, Jashank. I've done that also in other situations using hard links. So thank you. In fact, that might be the last time I really used hard links for anything significant.
Sorry, I kind of confused myself with permissions. What I meant to say was you can have a file behind a directory that you haven't got permission to, but access it from another link.
All right. So that's hard links. You can see this by the way that a file has multiple names in the file system. Yeah, it's a weird thing. It's not a significant thing. It's interesting in that a file is only destroyed when the last link to its INO number is removed, when its last hard link is removed. You can't hard link directories. That would create would make file system semantics too complicated. And hard links must be on the same file system. They're based on I numbers, so they must be on the same file system. Alright, so I've said I haven't used hard links for ages, and the last time I did was deduplicating a set of directories. I had a large set of directory with millions of files, many of which were copies of each other, and I wrote a program that made all the copies links to one version of the file. That's called deduplication. Companies like Dropbox, for example, rely on that very heavily because many users upload the same files and prefer not to store multiple copies of the same file. Alright, so hard links, yeah, not exciting. Symbolic links, incredibly useful. Use symbolic links almost daily. They give you a pointer. They give you a way of saying, go here. So they say this name is a reference to this name. Why would you use symbolic links? Let me show you. So use for symbolic links, the classic use for symbolic links from this morning. So I accidentally told everyone yesterday's lecture code examples would go in week 06 Tuesday. I forgot this was now week 07. So I thought, oh well, I'll move that directory to the correct name, which is this, because students might be looking for it under the correct name, week 07 Tuesday. But then I was thinking, oh no, what about the students who've got the old email which has the wrong name in it? They'll go to the wrong name. What do I do? The answer is I can make both names work. I can say week 07, I moved the directory to its right name, then I created a symlink, and the symbolic link I created by doing, I have to put an F there because it already exists. I said make week 06, oh sorry, that's Tuesday, make it point to this. And that creates this object in the file system. Oh, how can I tell it's a symbolic link? Look over here. There's an L there. I guess while we're looking at ls output, there's a few things there, isn't there? There's a D and all the others saying they're directories. These are permissions here. So the first three are what the owner of the file can do. The owner is me. The next three are what people in the group. We're not going to get into groups. The last three are what anyone can do. And that's the sort of classic sort of permissions you might see. I'm the only person who can change the file, but I'll let anyone else write to it. Sorry, read it. In this case, it's a directory, so this directory, anyone on a CSC system, when it's copied to a CSC system, can look at the files in the directory, but I'm the only person who can add files to the directory. The permissions on symlinks don't mean anything, so there. Let's go down back to while we're working, and let's look at this for the files in the directory where we're working. Here you can see the size in bytes of the file, and it's printing out a timestamp. There are a couple of timestamps associated with files, often 3 timestamps, perhaps more on a Unix-like system. This timestamp is when the file was last changed. Enormously useful if you're wondering, if you look at this and say, oh, it was compiled at 1251, but have I changed the file later? So get into the habit of looking at file modify times, trying to understand what's happening. Have I changed this since I did this? When did I download this, and so on. File modifying times, enormously useful. Alright, so that's symbolic links. We will show you programs with symbolic links. I don't think we'll get them in today's lecture.
Oh, that's a good question. Executing a file makes sense. What does executing a directory mean?
Oh, yes. All right. Executing. So, read permission on a directory means you can see the names of all the files in the directory. Executing means you're allowed to access the directories, but you're not allowed to be. You can't see the names in the directories. Normally, you'd have both. If people can access the files in the directory, you'd let them find out the names of the files in the directory as well. But sometimes we want to be clever, and we use names that people can't guess or something like this, and then we give people only permissions to access the directory. So then if they know the name, they can access the file, but if they don't know the name, they can't access the file. So then we can use the name as a key to access a file. There we go. So that's showing you using ln to create a hard link and a symbolic link, and I've said symbolic links are the ones we'll normally do, and that's how a symbolic link prints out in LS. You can play with those yourselves. That's excellent thing to do. Try create some files and play with them yourselves. Maybe after you've got the assignment done. Alright, there'll be 2 things. If you're doing this on your own computer, make sure you've got backups or working with files so they're not your assignment. Don't play with file system commands with valuable files. And have backups. So, alright, let's go into what I can do with a file. How do I work with files on a Unix-like system, talking to the operating system? First, system calls manipulate file system objects as a stream of bytes. I can be sending bytes to a file in a stream or getting bytes from a file in a stream. In my transactions with my operating system, with my system calls to the operating system, I might have multiple streams of bytes coming and going. We've already seen that, I think, here. So we've seen this program here has a stream of bytes coming in and a stream of bytes going out. 2 streams. But a program could have 5, 10, 50, 100, perhaps more streams. There is a limit. The limit's usually the order of 1,000, 2,000, something like that. I think it's actually configurable these days. But so I've got to say, I've got to identify to the operating system which stream I'm talking about. It is possible to have multiple streams of bytes coming from the same file, so I can't use the file name to identify the stream. And I need a simple way to do it anyway, the simple way is a file descriptor. What really is a file descriptor? It's just a tiny integer. It'll be indexed to an array in the operating system. So for every running program, the operating system will track what streams of bytes it's got happening now. And it might just be, for a lot of the programs you've been writing in this course or in COMP1521, it might be just 2 or 3 streams, so the array might be tiny. So a file descriptor is just a small integer, indexes this array, so it tells you which stream we're talking about. If I open a file system object, I get back a file descriptor. So the open is the system call to say I want to get or send bytes to this file. I get back a file descriptor that will allow me to do this. When I'm done with it, it's a good thing to do is to say close, which says I'm done with that file descriptor. Destroy this file descriptor. Why is that good? File descriptors are a finite resource, so if I have a program that's opening millions of files, it will run out of file descriptors after it when it's got more than 1,000 open. So when it's done with a file descriptor, it should close it. Read, yeah, right, we've talked about. lseek is an interesting one. It removes our file descriptor's position in the file. And stat is a different system call, not associated with file descriptors, which gives us metadata. So there's a nice set of system calls to manipulate files. But these, by the way, are the names of the C wrapper functions. So rather than work, well, I'll show you. Let's look at some examples. Exactly. Let's go to the next one. Oh, all right. Hopefully this is I think this might be our last example where we're doing raw system calls. We'll show you nicer ways of doing this, but this is the raw system calls showing you not quite the bare metal, but the operating system interface at almost its most primitive to do CP. So you've used the CP command to copy a file. This is how you do that with raw system calls. The system call we need is system call number 2, open. It gives us back a file descriptor. So if I want to do, what do we call it? clang cp syscalls. So I'll call it mycp. And I want to run mycp and copy, I don't know, we'll copy lseek.c to, there we go. Alright, so I'm doing this. The file I want to copy is argument 1, argv1. So I say to open, give me a file descriptor accessing this path name. Notice I can give just a relative path name. The operating system will look at my current working directory and use that to find the file I'm talking about. So I've said open, I say a path name. I've got to give it 2 more pieces of information. Open is, well, I'd say you'd almost say it was overloaded. I'm not sure if open design is great like this. It's been like this a long way. Yeah, maybe it's sensible. It's used for a few things, so I have to say what I want to do with the file. And there are drastically different operations. So like open can be, you can open a file to change it or to get its bytes, to send bytes to it or get its bytes from it, or both. I guess the idea you can do both is sort of means it's a sensible design. So the third argument there says what I want to do with the file. It's a bitmap. and it turns out a 0 bitmap means I just want to read from the file. And then if a file gets created, what its permissions will be is the remaining argument. So I say read from my first argument, write to the file as my second argument, and then down here, when I do a read system call, I pass whatever file descriptor I got there, and when I do a write system call, I pass that, and I can get bytes from one file and send them to the other with those system calls, and that should have created a copy of lseek.c. Actually, let's do something insane. Let's call it to look at this. I've created a copy of a file by doing ugly, low-level, horrible system calls, but I've done it the hard way. Alright. Have I got an easier way to do this? Alright. So the good news is, I think this is goodbye to this ugly, low-level syscall thing. So that was to show us, what a raw system call looks like. From now on, we'll go up a level. Every Linux system call has a C function wrapping around it. Well, pretty much every system call. Sometimes new system calls don't have one yet, but all the commonly used Linux system calls have a C function wrapping around it, which is much more convenient to use. So, for example, the write system call has a function called write, which wraps around it. Much nicer to use. I can access it there. And this is my program saying hello Andrew with a write system call. This is the copying standard in to standard out using the write and read. So the wrappers around read. So this is more normal programming. This is not actually the best way to write this code. If you're doing Linux dependent things, you'd use these functions, but there are higher level functions still that you would normally use for I/O. But this is better. So this is using read to do a read system call and write to do a write system calls. These are little C wrappers that just make using the system calls more convenient. These might be just tiny wrappers around the syscall function. And the one I wanted to see is this one. This one makes it a bit more obvious what's happening with read or write. This is me getting a read file descriptor by opening the first argument of the program, first command line argument, getting a write file descriptor from opening the second line there, and sitting in a loop going backwards and forwards, copying bytes from one file to another. Well, that's nice. Alright. Yeah. So be aware, open, read, write, close, not so portable. There are many platforms that give you a C compiler that don't give you open, read, write, and close. So you might go down to you might have a little embedded processor, a PIC or a similar device, and it won't. The libraries that you've got there won't give you open, read, and write and close. So that being said, POSIX does standardize them to some extent, and you might get implementations on Unix, on non-Unix systems. It's better to use functions we'll get to from stdio.h. Pretty much every C implementation implements those, and so you can write programs that just work everywhere. And there's not really any much benefit normally if you're to go using open, read, and write. So you're just safer staying at stdio.h. There are exceptions where you want the low-level functions, but they're exceptions.
Not only safer, but also way faster, because it does a lot of clever caching and buffering that you probably won't be implementing yourself.
We get, for talking about files, some more integer types. Sorry, they're not. I know it's a little confusing, but they're nothing really special. So there's a few. When you look at the definitions of a few of these functions of manipulating files, there's some extra types there. So they're just integer types. So one is off_t, which will typically be 64-bit signed. It's a direction in a file. It says go forwards or backwards. You'll often typically encode it with the type will be off_t, and it's typically 64 signed. You sometimes might have to supply the number of bytes in some object. That'll be unsigned, and there's a signed version if for such a value coming back from a system call, which includes the possibility of errors. Another type we're going to get familiar with is a struct called struct stat, which is essentially gives you the contents of an inode. Well, most of the contents of an inode. It gives you metadata about the file. It doesn't give you its contents. It gives you information like you could decode from it when the file was last modified, who the owner of it is, and so on. Don't worry too much about these sort of things. If they're ever needed, you'll be able to look at, we'll either give it to you or you'll be able to look these up. These are not things you have to memorize. The important thing, I guess, to remember to note is these are just numeric types, and they're probably 64-bit numeric types on systems you're likely to be using now. So let's look in more detail at Open. So this is the C library function that wraps around the Open system call. You give it a path name, and you give it some extra information. The extra information is actually, and it's one of the reasons we covered bit operations early in this course, supplied as bit level values ordered together. So if I want to write to a file and create it if it doesn't exist, the value I have to supply as the second parameter is these two values ordered together. If you look at the raw values, these will be, we had that Pokemon example way back. Look back at the Pokemon example we did of the sets of Pokemon way back before MIPS. So Open uses bits as Boolean values, and you set a certain bit if you want to append to a file, you set another bit if you want to read and write to the file, set a bit if you want to create a file, set a bit if you want to truncate the file to zero length if it already exists. There are some other possibilities there. They're just the classic ones. Two possibilities coming back from Open. You'll get a file descriptor, a small positive integer, or you'll get -1 indicating an error has occurred. Okay, now this gets a little weird. If an error has occurred, no, it's a lot weird. A special variable is set in your program that you didn't even know you had to say what the error was. We'll look at how you access that. And don't even ask what happens if you have a multi-threaded program. Alright, Open is sort of weird and complicated. Close is so easy. If only everything was as easy as close. You just give it the file descriptor and it closes. It does return something, but not many people actually even check the close return code. You just send it off and hope it works, because there's often not much you can do if a close has failed anyway.
It's like, oh look, my close failed. Well, I can't do it again. So that's nice to know.
There is one weird thing. If this is weird facts. Well, no, it can be an important fact. If running programs have a file open and it gets all its names get removed, say with RM, The file still stays around until the last process closes their file descriptor. Then and only then is the file, operating system cleans up the file resources. So there are neat library functions that use this trick for temporary files. A program wants a temporary file and they don't want to go to the trouble of cleaning it up. What the library function does is opens the file for it and then removes the file and says, here's your file descriptor. When you close this file descriptor or exit, the file will disappear. Don't worry too much about that. So there, this is sort of this is an advanced topic. But close, beautiful simple function. We like close. Read. We've already seen it in an ugly form. This is in a more beautiful form. Read bytes to this memory location. So read up to count bytes to this memory location. Void is a generic pointer in C. I'm not entirely sure why that's void rather than unsigned char, which would be the type I would pick. Maybe on platforms where
basically the compiler ignores casting if you have a void. You can automatically cast a void without errors.
The other advantage here would be that void star implies that you must cast to another type to get something useful out of this, because dereferencing void star gives you a value of type void, which is a contradiction.
All right. So read returns how many bytes it read, which is this weird type we saw, which is probably int64 underscore t, assigned 64-bit value. Yes, you may be able to ask for more than 2 to the 32 bytes. You may be able to get more than 2 to the 32 bytes. Never actually tried that. I probably should. It will return 0 if it couldn't read any bytes. It will return -1 if there's some error, and this weird variable erno gets set to the reason for the error. Now, an absolutely crucial piece of information is associated with a file descriptor is a current position in the file. What that means is if you call read and say give me 1,000 bytes, you'll get the first 1,000 bytes in the file. If you say read again for the same file descriptor 1,000 bytes, you'll get the next 1,000 bytes. So the file descriptor knows you're up to byte 3,000, and will give you bytes 3,000 to 4,000. Or you're up to byte. File descriptor knows you're up to position 4,000, and you ask for 1,000, you get bytes 4,000 to 5,000. So there's a current index. It knows you're up to byte in the file, and you do a read. You get bytes from then on in the file. So you can just sit in a loop, repeatedly reading, and get the entire contents of the file. You're saying, I'm too cool to do that. I want to do something else. I want to go backwards and forwards in the file. lseek is your friend. You can use lseek to modify where you're at. So you can change what the current position is. Right, it's pretty similar, very similar, except I say here's a memory address, write count bytes from that memory address to this stream, and it gives you back a number, which is how many bytes it managed to write, which will probably be that number or -1. Again, there's a current position, so repeated calls to write can be used to create a file. So you might make 10 calls to write, each adding 1,000 bytes to a file. Again, you can change the position with lseek and move about a file, changing bytes at random position if you want. Oh, that's the one we've just seen. And this is read bytes from standard input and write them to standard output. And this is CP, reading from a file and writing to another file. Right. I should say there's something really bad in this code, and I've done it so it all fits on a lecture slide. You remember I gave you a rule in life, some life advice that will make your life happier. I've given you a few probably, but one of them was every time you index an array, asking yourself, how do I know that index is valid? And if you can't prove to yourself in your head the index is valid, you should be adding code to your program. You should be doing something. My next piece of life advice would be every time you make an operating system request, check the result. Even if you're like 100% sure it's going to succeed, you should check the result. Assert, by the way, is a great way to check the result if you think you're sure it's going to work. So
I have some formal methods people here who would like to object to your use of assert. I'm
sure they would, and they, unfortunately, it's my lecture, so they can't. All right, there are. Well, I know. I actually think this is sort of a rational way to use assert. Yeah, I've seen people complain about this, and they say that you're too lazy. Yeah, it is being lazy, but it's better than the alternative. Let me tell you. So I might assert that this is this. I'm sure this file is always going to exist. I'll assert that. In practice, these beliefs they always break on you. And if you don't check the operating system return call in at least some way, a better way is with an if and an error message. So if, and then do something. A better way is that if you don't do this check, then your program trundles on, and the worst possibility is that it'll then do bad things, it'll do destructive things, it'll destroy data, you'll lose files, you'll lose things. It's quite possible to lose a lot of stuff once you start writing programs to manipulate files. Even the best case is you'll get incomprehensible messages. So you'll make life better for, well, if not future you, future someone, if you put at least a minimal check every time you talk to the operating system. Because no matter how sure you are it's going to succeed, there will always be some circumstances it won't. Maybe you're thinking, I'll always be able to write this file and the file system will be full. The file system will be read-only. Something like this. Something won't be mounted. There's always something that will break. All right. So to fit this, to fit this code in lectures, I've skipped those checks. Okay. What have we got now? Oh, we're going to skip whatever changes we made. Oh, do I want to show this? Well, maybe I don't want to show. Sorry, let me go back to my slides then. Last one I want to show you for today, last function I want to show you for today, lseek. Change the position. So what do we do with lseek? 3 arguments. First, file descriptor. The file descriptor we want to change the position of. Then we want to say how we want to change it. Can be a positive number, can be negative. So we can say go back 10 bytes, go forward 50 bytes. So we can say a number of things. Third argument has the lovely word whence, which we don't hear very much these days. Whence. And we can say, look, I'm talking absolute in the file. So I'm giving you a positive number, which is a position in the file. Could be 0, could be 5. I can say go to byte 1,000,000 in the file, set the current position to byte 1,000,000 in the file. I can say relative. Go relative to where I am now. Change the current position plus 10 or minus 20. Go relative to where I am now. And I can also say relative to the end of the file, and that's quite useful. I can say go 0 from the end of the file, or go minus 20 from the end of the file. So in this case, if I use this will always be positive, this will always be negative or 0. Okay. So that's seek. Let's try and look at this. I don't want to look at these ones. I want to do I've got an example here. I think I've got L seek. Yeah, this is what I wanted to show you. Perfect. Let me just compile this. We can compile with DCC. The syscall things, well, I wasn't compiling with DCC. I wasn't sure how well DCC plays with syscalls. We'll just run this A.out, that's fine. Alright, so I can say, give me the first byte of which file? Oh, A.out. Hey, oh no, that would be silly. Alright, we'll say with this file. So it's told me various bytes from this file. First byte, last byte, 42nd byte, 100th byte. Ooh, last byte in this file is a new line. Interesting. Not really. How did this all work? I want to print the last byte. First, open the file. I've been given the file as an argument. I say, look, I'm going to be reading that file, open it. I've got create an array that can just hold 1 byte. We're going to be doing 1 byte reads. If I just did this read without the lseek before it, I'd get the first byte in the file. So the current position in the file starts out at the start of the file. But I don't want that. I want to make the current position 1 before the end of the file.
That
so I say,
depends on how you open the file, where the file pointer starts.
Oh, that's true. If you open it for writing and appending, you'll start at the end of the file. Yeah, that's true. But all right, in this sort of the typical way you open it to read a file like that, you start at the start of the file. And then I do a read, and it's giving me the last byte of the file, which is the new line of the last byte of the file. If now I want to read if I do another read now, it would fail because I'm at the end of the file. The current position is at the end of the file. I would get back 0 as bytes read. But I can now say, look, make the current position the start of the file. So seek set says do it relative to the start of the file, and I'm saying 0 bytes from the start of the file. This gives me the first byte in the file, and then for fun I can then read other bytes in the file. So they're using it to, and there's last one is doing a relative seek. So
you said that reading past the end of a file would fail. What about seeking past the end of the file?
Seeking past the end of the file in read mode will fail, I think. Yeah, no, it should return an error surely. Seeking past the end of the file in a write mode does more interesting things, which we'll cover in a lab exercise. It creates empty gaps in the file. It's really quite bizarre. I've got an example for that, but we won't get that today. Actually, I'll put up the example. I'm going to come back to this in the next lecture. No, actually no, it does different things as well. Anyway, all right. No, I don't want to see this example today. All right. This is a good point to finish the lecture, because the next part I'm going to talk about moving a level up in doing I/O and how we do that. So we'll do that in the next lecture. All right. Good luck with finishing off the assignment. We'll try to put on extra tutors on forum, extra tutors on help sessions. Please be patient. As I said, the forum questions in the forum are at record levels, and the tutors are busy doing other things, but we'll try and find as many people we can to help you with finishing off the assignment. Again, a reminder, if you need interactive sort of help, you've got sort of general problems, maybe a help session. If you've got specific issues, my SPIM prints out this weird message. What does it mean? Yeah, great, in the help session. All right, thank you all very much for joining this lecture. I'll see you on next Tuesday for more on files, and next Tuesday's next week's lab will be file operations. So you'll get to try out all of these operations and reading and creating files and manipulating files. So we'll get you doing that in next week's lab. So see you next Tuesday.